Welcome to the Cumulus Networks video series on OpenStack. In this edition, we're going to talk about spine and leaf networks and how to build an OpenStack undercloud, or the bare metal physical network components for an OpenStack infrastructure. Whenever we look at building networks within the data center, whether it's for OpenStack or any other application, almost all deployments are based on spine and leaf deployments, also sometimes called a CLOS. So we call spine and leaf networks because we describe the top of rack switches as leafs, and the end of row or network only switches as spines. When building a spine and leaf network, spines never connect to each other. However, every spine will connect to every leaf. It's extremely common in all enterprise deployments, whether it's OpenStack or otherwise, to deploy leafs in redundant pairs and use MLAG, or as Cisco calls it, VPC, to a server. It is allowed to interconnect those leafs for that MLAG or VPC connection. However, no other leaf-to-leaf connections will exist in the environment. One of the beautiful things about a spine and leaf network is that just like OpenStack has a scale-out architecture so that I can grow my cloud as my needs grow, I can do the exact same thing for a spine and leaf network. So first off, if I need to add additional compute capacity and roll in another rack of servers, I can simply deploy another pair of leafs with all of the servers connected below them, and then interconnect those leaves to my spines just like any other leaf in the environment. Extremely simple to scale out that network connectivity. The other component within a spine and leaf network is what we call the oversubscription ratio. So the oversubscription ratio is measured by the amount of bandwidth within a rack divided by the amount of bandwidth out of the rack. It's very common to see oversubscription ratios from anywhere from 1:1 to 3 or 4:1 in the data center. Most of the oversubscription ratios that we see are in the 2:1 or 3:1 range. So as an example, if I have 48 10 gig servers, this is 480 gigs within the rack. And if I have 3 100 gig uplinks, this is 300 gigabits of connectivity out of the rack. So my oversubscription ratio is a measurement of the ratio of uplink capacity against downlink capacity. If I need to expand out the amount of bandwidth in this environment, I can simply add another spine. And I'll connect in that spine just like every other spine. So I simply connect to every leaf in the environment. And I've now changed this from 3 by 100 to 4 by 100 gig, reducing that oversubscription ratio and giving me more bandwidth in the core. Another important characteristic of spine and leaf networks is the use of layer 3 routing between the spine and leaves. In traditional 3-tier architectures with an access, a distribution, and a core, we would use regular layer 2 with spanning tree or with MLAG at all layers to provide connectivity. However, we're limited to only 2 uplinks in those environments, and we lack that ability to do scale out bandwidth growth within the core. So by using layer 3 routing, I gain the ability to use equal cost multipathing and be able to use 3, 4, or 16 spines. However many spines I have, I can load share my traffic out of a leaf across all of those spines based on routing. In previous videos, we've talked about VLANs and VXLANs for tenant isolation and layer 2 extension. With regular VLANs, I cannot use a layer 3 ECMP fabric within a spine and leaf network. However, with layer 3 and VXLAN, I can achieve all of those components where I can use a layer 3 fabric while still providing layer 2 connectivity between tenants in my environment. So it's important to remember VLANs require a layer 2 network, while VXLANs can work over a layer 3 network while providing all of the same characteristics and capabilities. So this has been an overview of building spine and leaf or CLOS networks within an OpenStack environment or any private cloud infrastructure. And look to the other videos in this series to talk about things like EVPN, an overview of OpenStack, or comparing VLANs and VXLANs in an OpenStack deployment.